Hi, I'm Keenan Casey for TouchPlus.com. In this lesson of Machine Learning Distilled, we're going to look at feed-forward neural networks, something that's also called artificial neural nets. The feed-forward neural network is an algorithm that's inspired by biology, inspired by the biological brain. It's really an extension of the perceptron that we've already looked at. By combining several perceptrons together allows us to model nonlinear functions. We'll also discuss the backpropagation algorithm, a very important algorithm that trains neural networks. These are the terms we'll be using in this lesson. The input will be a vector x. The output may also be a vector, or it could be a simple value. We'll call the output y. We'll have our training instances, which are x, y's, the one vector that contains input and output, and our training set is the set of all of the inputs and outputs all organized together. There are n features, that is, there are n columns, that's the length of the x input values, and there are m training instances, so that's the number of rows in our data set. Neural nets are usually used for regression, but they can be adapted and used for classification as well. Recall the perceptron. It's a simple linear model that computes the product of input and a weight, sums that up, and pushes it through a sign function to get a 1 or a -1. We use perceptrons for classification. We're going to reconfigure the perceptron and evolve it into a feed-forward neural network, which is really a multi-layer perceptron. As you recall, the sign function is a really simple function that returns -1 if the value input is less than 0, +1 if it's a value greater than 0. We did this to do classification using a perceptron. Well, let's tweak this so we can make it a neural network, which is really a multi-layer perceptron. First, we're going to change this unit from a sign function to what we're going to call an activation function. We'd like this activation function to go from 0 to 1, but do so smoothly instead of that really harsh discontinuous sign function. We're going to call this function h of x because it's going to be hidden. Next, we're going to collapse our notation a bit, and instead of showing those weights, we'll just put the weights on these lines that connect the input units to this summing unit. Next, we're going to replicate this perceptron, the sum, the h, and the output, several times. Additionally, we're going to have weights that connect every input unit to each of these summing units. So now these weights are a weight I, j, where I is the index of the input and j is the index of the summing unit. The next step in converting the perceptron to the multi-layer perceptron is to actually add an additional layer. In this diagram, you see that we've replicated the weights, the sum, and the hidden function into a second layer. So now the output from this layer is the input to this layer. And these are weighted with a different set of weights, which we've noted v of j, k, where j is the index of this hidden unit and k is the index of these summing units. So this is our feed-forward neural net. We've converted the perceptron into this feed-forward neural network. And let me show you, starting from scratch, how a feed-forward neural network works. As we said, the FFNN is really a multi-layer perceptron. We'll start with x question mark, which is some unknown input. This gets split out into the components of the vector, in this case 3. That's called the input layer. Next, there's the hidden layer, which is those hidden functions. These are all connected by weights, so this value gets multiplied by this weight and input into this hidden layer, which really sums all of the weights coming in and puts it through the hidden function. These two layers are fully connected, so that means there's weights that connect all of them. After the hidden layer, there's an output layer, which is really just like the hidden layer, but it has different weights connecting it. In this case, this v sub j, k. These two layers are also fully connected. The output layer then, the result of it is our output vector y sub question mark. Let's take a look at what the input and output to each layer is. First, the input to the hidden layer. In this case, the input is simply the product of x sub I and the weight on each link. We sum those up, and that sum, which I've called capital H sub j, is the sum that goes into each of these hidden units. It's sub j because the hidden layer units are indexed by j. The output of this function is simply this function, h of x. It's also called the sigmoid function. Really, then our output will just be the hidden function with an input of hj, as shown here. Next, let's consider the input and output to the output layer. So the input to the output layer is simply the output of this hidden layer. We're going to call this capital H sub k. What we've got here is the product of the output of the hidden layer times the weights. And we sum all those up, but that's the input at this output layer. The output of the output layer, which will be the final output of the neural net, is this same hidden function again, in this case applied to H sub k. So this is the way a feed-forward neural network is structured and the way the data flows through it. You can see why it's called a multi-layer perceptron, because it's as if we have two layers of multiple perceptrons in each layer. Now let's consider the pseudocode for a feed-forward neural network. First, we compute the input hidden layer. For each node I in the input layer, we iterate over it and iterate over each node j in the hidden layer. We then compute the input, which I've called input sub j, and it's just the sum of the weight times the current value of x. The output is simply the hidden function applied to the input sub j. So we'll have output j for every hidden node unit. So this is our first set of for loops that computes the input to hidden portion. Next, we have to compute the hidden to output portion of the neural net. For each node j in the hidden layer, we'll iterate over it and then iterate over each node k in the output layer. We'll simply compute the input by summing up product of the v weight vector times the output sub j, and then we'll compute the complete output as the hidden function of I sub k. So this is a pretty simple computational process to push data forward through the network. You see why it's called a feed-forward neural net, because the data makes its way layer by layer through the neural network. Now let's also note that it's possible to create neural nets with more than one hidden layer. In this case, we've got two hidden layers. By doing this, we're going to need a whole new set of weights. In this case, W, V, and U. We'll need a different set of weights between every layer. Adding more hidden layers increases the complexity of the network, but it also allows us to model more complex functions. The interesting thing about neural nets is that they can approximate any function. With one hidden layer, they can approximate any continuous function. And with two hidden layers, they can even approximate discontinuous functions, as long as they have enough data. Now the question we always end up asking is, how do we find these weights? If all the magic is in the weights, how do we find the weights? Well, the nice thing about neural nets is there is a well-defined algorithm that's mathematically based to learn these weights. The way this algorithm works is a training instance is selected from the data set and input that is pushed forward through the neural network. When the output is computed, the squared error is computed. That's just the difference between the correct output and what we predicted. We square that. We then propagate the error backwards through the network and assign corrections to the weights and update them so that they'll do better next time. We then repeat this over and over again until we get an error that is acceptable. Here's a visual overview of the backpropagation algorithm. We start with our input vector, x. These values get pushed through the weights to the hidden layer, summed and pushed through the activation function. The output from the hidden layer gets pushed through the weights and is input to the output layer, which then outputs the current guess for the output. And that's going to be wrong, and we're going to compute the error by simply computing what we predicted minus what was correct. We know the correct value because it's in our data set. Once we've computed the squared error, we propagate that error backwards through the output layer to the weights and adjust those weights appropriately. Go through the hidden layer and compute the update to the weights from the input to hidden layer. Once we've updated the weights, we select the next training instance and propagate it forward through the network. And then, once we've pushed it through the network, we figure out a new error and push the error back through. And by iteratively doing this, we're able to update the weights to the correct values that it will actually map our input to our output. Now let's consider the pseudocode for the backpropagation algorithm. First, we initialize the weights, typically in a random way. We then start a do loop. And for every instance x in the training set, we push forward. We compute the neural net output for that instance x. We take the desired output for that instance Then, on the backwards pass, we compute the error, which is d minus o. We square it and compute the deltas, that is, the differences for the weights from the hidden to the output layer, based on those values. We then compute the deltas for the W weight vectors, that is, the weights from the input to hidden layer, and update all of the weights. We'll continue doing this iteratively over the training set until some stopping criterion is satisfied. Example of criteria that would cause the algorithm to stop are that all the examples have been classified correctly, or if we're doing regression, we have some acceptably small error. We may also limit this to a maximum number of iterations. Maybe we only do 100 repetitions through the data set. Or another reason to stop might be if there's no change in the error from one iteration to the next. We've kind of reached the minimum that we can find. When we've done this, we'll return our neural network, which is really the set of weights, is what we found. Let's consider backpropagation as a flowchart. As I said, we first choose random weight sets, W and V. We'll compute the output of the neural net using some training instance, X sub I. After we've done that, we use the backpropagation algorithm. If the error is small enough, then we'll be done. If it's not, then we increment I, that is, go to the next training instance and compute its output and go back into backpropagation. So let's look at what goes on inside backpropagation in a little bit more detail. First, we compute the error of the output layer. We then update the weights of the hidden to output links, that's the V weights. After that, we compute the error of the hidden layer, and then update the weights of the input to hidden links, that's the W weights. A neural network is really defined by its architecture, and there are several components of the architecture. For one, the number of neurons per layer. Number two, the number of hidden layers. As I've said, we can put in one hidden layer and approximate continuous function, or two or more to approximate discontinuous functions. Also, the number of connections between each layer will define the architecture. Most neural nets are fully connected. Let's summarize the strengths and weaknesses of neural nets. First of all, they're computationally efficient to use. Once you have it created, it's pretty easy to use. The backpropagation algorithm is an elegant algorithm that actually works to learn the correct weights to model some mapping. Another strength is we have the ability to vary the complexity of the model by changing the architecture. That is, the number of hidden units, the number of layers, and so forth. In the weaknesses, however, we have a very computationally expensive and therefore slow training process. Secondly, neural nets are prone to overfitting. That is, they're not great at generalization because with very large complex architectures, they can really completely memorize the data and even learn the noise so they don't generalize outside of that data set very well. And thirdly, neural nets are not interpretable. Once you have one created, you can't look at it and understand why it's producing the output that it is. When you have a neural network, you really have this set of weights. And when you get the result from the neural net, there's no way to interpret why it produced that result. This is as opposed to, say, a decision tree or naive Bayes where you have probability or you have a set of rules that you can clearly understand as a human being. Finally, let's consider the representation, evaluation, and optimization for neural nets. First, they're represented by the architecture, a set of weights, and the activation function. Typically, neural nets are evaluated using the sum squared error, which is just the predicted minus actual squared, and summing that up over the whole data set. And the optimization is done using the backpropagation algorithm. In this lesson, we've looked at neural networks, specifically feed-forward neural nets. They're a type of regression algorithm that also be applied to classification. They are a form of supervised learning. We're predicting output based on input. I'm Keenan Casey for Tuts Plus. Thank you for watching.